Welcome to this walkthrough of problem number 1411, number of ways to paint n times 3 grid. In this session, we'll explore how to solve this interesting combinatorics problem, discuss different approaches, and analyze their efficiency. Let's dive in. The problem involves an n times 3 grid, where n is the number of rows, and each cell in the grid must be painted using one of three colors: red, green, or blue. The key restriction is that no two adjacent cells can have the same color. Adjacency applies both horizontally within the same row and vertically between rows. Your task is to determine the total number of valid ways to paint this grid while respecting these adjacency rules. Since the number of possible configurations can grow very large, the result must be returned modulo 10 to the power of 9 plus 7. For the input, you are given an integer n, which represents the number of rows, and it will range from 1 to 5,000. The output will be a single integer representing the number of valid ways to paint the grid. For example, if n equals 1, we are working with a grid that has only one row and 3 columns. There are exactly 12 valid ways to paint this grid. Each cell in the row can be colored red, green, or blue, but no two adjacent cells can share the same color. Some valid configurations include red-green-blue, blue-red-green, and green-blue-red. When we enumerate all possible combinations that satisfy these constraints, we find there are 12 in total. Now, let's consider a slightly larger grid with n equals 2, where there are 2 rows and 3 columns. The output for this case is 54. When n equals 2, the number of valid ways increases because we now have to consider adjacency rules not only within each row but also between rows. The first row can still be painted in 12 valid ways, as calculated earlier. For each valid pattern in the first row, the second row can be painted in a way that respects the adjacency rules both within the row and with the row above it. For example, if the first row is painted red-green-blue, the second row could be green-blue-red, but it cannot be red-red-green since the adjacent cells in the second row would have the same color. Taking all these combinations into account, there are 54 valid ways to paint the grid when n equals 2. Similarly, when n equals 3, the number of valid configurations grows exponentially. For n equals 3, we have 3 rows and 3 columns. The output for this case is 246 valid ways to paint the grid. This rapid increase in the number of valid configurations highlights the complexity introduced by the adjacency rules as the grid grows taller. The constraints require us to ensure that every row in the grid respects the horizontal adjacency rules while also ensuring that every pair of adjacent rows respects the vertical adjacency rules. With this exponential growth in possibilities, it becomes clear that we need an efficient approach to calculate the result for larger values of n, especially since the upper limit for n is 5,000. This is where the constraints and key observations become important. The constraints for this problem emphasize the need for efficiency. First, the grid has a fixed width of 3 columns, and the number of rows can be as large as 5,000. This makes brute forcing through all possible configurations computationally infeasible. Modular arithmetic is required to keep the results manageable and to prevent overflow, as the result must be returned modulo 10 to the power of 9 plus 7. A key observation is that row patterns can be categorized into 2 types: Type A, where all 3 cells in a row have distinct colors, and Type B, where 2 cells share a color, and the third is different. Using dynamic programming, we can calculate the valid configurations of each row type and propagate these values efficiently across n rows. This approach allows us to handle edge cases, such as grids with a single row or the maximum number of rows, within a reasonable time. To begin, let's consider the brute force approach. The intuition here is straightforward. For an n times 3 grid, we attempt every possible combination of colors row by row. This involves ensuring that no two adjacent cells, whether horizontal or vertical, violate the rules of the problem. We could use recursion or backtracking to systematically generate all valid configurations and then verify each one. However, this approach quickly becomes computationally expensive. For each row, there are 27 possible color combinations since each cell has 3 color options, and there are 3 cells per row. But many of these combinations fail the constraints, so the number of valid grids is smaller. Despite that, the number of combinations grows exponentially with n, leading to a time complexity of about 0.27 to the power of n. This makes the brute force approach infeasible for large grids, such as when n is 10,000, due to the sheer computational burden involved. Now, let's shift our focus to the optimized approach we've chosen, dynamic programming, which is both efficient and scalable. The key insight here is that the coloring of any row depends only on the row directly above it. This dependency allows us to break the problem into smaller subproblems that we can solve iteratively. Upon further analysis, we find that there are only two distinct types of valid row patterns. The first type, type A, uses three distinct colors, for example, RGB or BGR. The second type, type B, uses only two colors, such as RRG or GGB. Here's the important part: the way we can paint the current row depends on whether the previous row is type A or type B. Specifically, a type A row can follow either a type A or a type B row, while a type B row can only follow a type A row. Using these dependencies, we define two states for the problem. The first state, A_I, represents the number of ways to paint row I as a type A row, and the second state, B_I, represents the number of ways to paint row I as a type B row. With the states defined, we can now establish the recurrence relations. The number of ways to paint row I as a type A row, A_I, is given by 2 times the number of type A rows in row I1, plus 2 times the number of type B rows in row I1. Similarly, the number of ways to paint row I as a type B row, B_I, is given by 2 times the number of type A rows in row I1, plus 3 times the number of type B rows in row I1. To compute these values iteratively, we start with the first row, where there are 6 ways to create a type A row and 6 ways to create a type B row, so A_1 equals 6 and B_1 equals 6. Using the recurrence relations, we then compute the values of A_I and B_I for all subsequent rows up to n. Finally, the total number of ways to paint the entire grid is simply the sum of A_n and B_n. This dynamic programming approach is highly efficient. With a time complexity of O(n), we only need to iterate through the rows once. The space complexity is O(1), because we only need to store the values for the previous row at each step. This makes the solution both time and memory efficient, even for very large values of n. Although the dynamic programming approach is efficient, it comes with certain trade-offs. Specifically, while it provides the total count of valid configurations, it doesn't generate the actual grid layouts. If we needed to enumerate all valid grids, we would have to use a different approach, such as backtracking, which would sacrifice efficiency for completeness. Now, the reason we chose dynamic programming for this problem is because it is perfectly suited to the constraints and structure of the grid. By reducing the problem to a recurrence relation involving just 2 states, type A and type B, we avoid the massive computational overhead of enumerating every possible grid configuration. This makes the solution highly scalable, even for the maximum constraint of n equal to 10,000. The simplicity of the recurrence relations, combined with the minimal memory usage, ensures that this approach is both elegant and practical for solving the problem at scale. In this problem, we are tasked with painting an n×3 grid using 3 colors, red, green, and blue. The key constraint is that no 2 adjacent cells, whether horizontally or vertically, can have the same color. This introduces both local and global adjacency constraints that we must carefully handle. To solve this, we need to calculate the total number of valid configurations for the grid. Now, let's start by understanding the constraints. Each cell has 3 possible colors, but adjacent cells cannot share the same color. This means that the number of configurations for a given row depends not only on the colors within that row but also on how it aligns with adjacent rows. For a single row grid, where n equals 1, each of the 3 cells can be painted under these rules. The first cell has 3 options, the second cell has 2 options since it cannot match the first, and the third cell has 2 options since it cannot match the second. This gives us 3 times 2 times 2 is equal to 12 valid ways to paint one row. When n is greater than 1, the configurations for subsequent rows depend on the patterns in the preceding row, making this a recursive problem. This dependency across rows is the core challenge we'll address in this algorithm. To tackle this problem for larger grids, we use dynamic programming to efficiently calculate the number of valid configurations. The first step is to define states that represent the relationship between consecutive rows. There are 2 key states, same_o and diff_o. The same_o state represents the number of ways to color a row such that its pattern is the same as the previous row, while the diff_o state represents the number of ways to color a row such that its pattern differs from the previous row. These states allow us to capture the constraints between rows and transition between them effectively. Next, we initialize the base case for n equals 1. For a single row, there are 6 valid configurations where no two adjacent cells within the row share the same color. These 6 configurations can be split into same_row equals 6 and diff_row equals 6, giving a total of 12 configurations. For grids with more than one row, the transitions between rows are determined by the adjacency rules. Specifically, the same_row state for the next row depends on both the same_row and diff_row states of the current row, and similarly, the diff_row state also depends on these two states. Transition formulas are derived as follows. The next same_row is calculated as 3 times the current same_row plus 2 times the current diff_row, while the next diff_row is 2 times the current same_row plus 2 times the current diff_row. These transitions ensure that all adjacency constraints are respected. With the transition relations defined, the next step is to iterate through all rows from 2 to n. At each step, we calculate the same_row and diff_row values for the current row based on the values from the previous row. This iterative process continues until we reach the nth row. By summing the same_row and diff_row values for the nth row, we obtain the total number of valid configurations for the entire grid. This approach highlights some key insights. Using dynamic programming allows us to break the problem into smaller subproblems, avoiding redundant calculations for overlapping subproblems. The state transitions are driven by the adjacency constraints, ensuring all configurations are valid. This method is also highly efficient, as it avoids the exponential complexity of generating and checking all possible grid configurations. Instead, the complexity is reduced to linear time, proportional to the number of rows, making it feasible to solve for large values of n. To implement this algorithm, we use 2 variables, same_row and diff_row, to track the number of valid configurations for the current row. This eliminates the need to store values for all rows, making the algorithm space efficient. Since we only rely on the previous row to compute the current one, the space complexity is reduced to O(1). In terms of complexity analysis, the time complexity is O(n), as we iterate through all rows and perform constant time operations for each. The space complexity is O(1), given the use of just 2 variables. This optimization ensures the algorithm scales efficiently even for very large grids. We must also consider edge cases. For example, when n equals 1, the algorithm should correctly return 12, as calculated in the base case. For large values of n, the algorithm must handle the computation without exceeding memory or time limits. Finally, for invalid inputs, such as n being non-positive, the result should be 0 since a grid cannot exist in those cases. This comprehensive approach ensures correctness, efficiency, and robustness across all scenarios. This implementation solves LeetCode problem number 1411, number of ways to paint n times 3 grid, efficiently using dynamic programming. The problem involves determining the number of valid ways to paint an n times 3 grid, adhering to the constraint that no two adjacent cells, horizontally or vertically, can have the same color. Each cell can be painted with one of 3 colors, red, green, or blue. ###explanation. 1. Initialization. We initialize 2 variables to represent the count of valid patterns for the first row. 2_color. This represents patterns where 2 adjacent cells share the same color, like RGB, RBG, etc. There are 6 such patterns. 3_color. This represents patterns where no 2 adjacent cells share the same color, like RGR, BRB, etc. There are also 6 such patterns for the first row. 2. Dynamic programming transition. For each subsequent row, we calculate the number of valid patterns based on the previous row's 2_color and 3_color counts. New_2_color. This is derived from the combinations of the previous row's patterns. Specifically, 2-color patterns can transition to 2 or 3-color patterns. 3-color patterns can transition to 2-color patterns. New_3_color. Similarly, this is computed as 2-color patterns can transition to 3-color patterns. 3-color patterns can transition to 3-color patterns. These transitions are weighted by how many valid configurations exist, and the results are taken modulo 10 caret 9 plus 7 to ensure numbers remain manageable. 3. Update in iteration. After computing the new counts, we update 2_color and 3_color for the next iteration, next row. For final result, after processing all rows, the total number of ways to paint the grid is the sum of 2_color and 3_color, taken modulo 10 caret 9 plus 7. This approach is highly efficient, operating in O, n, time and O, 1, space, as we only maintain two state variables to represent the counts for the current and previous rows. The solution is both optimal and scalable for large values of n. This Java implementation mirrors the logic of the Python solution provided earlier. The method number of ways calculates the total number of ways to paint the grid using 2-color and 3-color patterns, updating the counts iteratively for each row. Key differences include type declarations for variables, usage of long to handle large numbers, and Java's mod operation to prevent overflow. The final result is returned as an integer after modular arithmetic. To solve this problem, we start with the simplest case where n equals 1, meaning we only need to paint one row of the 3 times n grid. First, we initialize the constant mod, which is set to 10 to the power of 9 plus 7 to ensure our results stay within bounds for large calculations. Next, we define two categories of valid patterns, 2_color, which represents patterns with two colors in alternating positions like RGB, RBG, and so on, and 3_color, which represents patterns with three distinct colors, such as RGR or BGB. Both of these start with a count of 6 because there are 6 valid combinations for each category when painting just one row. Since n is 1, we only consider this initial row, and the total number of patterns is simply the sum of 2_color and 3_color, which gives us 6 plus 6 is equal to 12. Thus, the final output for this case is 12. Now, let's consider the case where n equals 2, which means we need to paint two rows of the 3 times n grid. The initialization remains the same, mod is set to 10 to the power of 9 plus 7, 2_color starts at 6, and 3_color also starts at 6. For the second row, we calculate the new counts based on the previous row's values. The formula for new_2_color is 2 times 2_color plus 2 times 3_color, all modulo mod. Plugging in the values, we get new_2_color equals 2 times 6 plus 2 times 6, which results in 24. Similarly, the formula for new_3_color is 2 times 2_color plus 3 times 3_color, again modulo mod. Substituting the values, we find new_3_color equals 2 times 6 plus 3 times 6, which gives us 30. With these calculations, the values are updated for the next row, 2_color becomes 24, and 3_color becomes 30. The total number of patterns for n equals 2 is then obtained by summing the updated values of 2_color and 3_color. Adding them together, we get 24 plus 30, which equals 54. This gives us the final output for n equals 2, which is 54. Now, let's examine the case where n equals 3. For this, we start with the same initialization, mod is 10 to the power of 9 plus 7, 2_color starts at 6, and 3_color also starts at 6. With n equal to 3, we'll need to calculate the pattern counts for two additional rows, using the relationships we established earlier. For the second row, the calculations are done the same way as before. The new_2_color is given by 2 times 2_color plus 2 times 3_color, modulo mod. Substituting the initial values, new_2_color equals 2 times 6 plus 2 times 6, which is 24. Similarly, new_3_color is calculated as 2 times 2_color plus 3 times 3_color, modulo mod. This gives us 2 times 6 plus 3 times 6, resulting in 30. At this point, 2_color is updated to 24, and 3_color is updated to 30. For the third row, we repeat the process with the updated values. The new_2_color becomes 2 times 2_color plus 2 times 3_color, modulo mod. Substituting the updated values, new_2_color equals 2 times 24 plus 2 times 30, which gives 108. The new_3_color is calculated as 2 times 2_color plus 3 times 3_color, modulo mod. This results in 2 times 24 plus 3 times 30, which equals 138. We then update 2_color to 108 and 3_color to 138 to prepare for any further rows. Finally, the total number of patterns for n equals 3 is calculated as the sum of 2_color and 3_color after the third row's updates. Adding them together, we have 108 plus 138, which equals 246. This gives us the final output for n equals 3, which is 246. By following this approach, we can efficiently calculate the number of ways to paint any n times 3 grid while ensuring the required constraints and patterns are satisfied. To determine the time complexity of our dynamic programming solution, we start by analyzing the operations involved. First, the initialization of 2_color and 3_color with constant values takes 1 time, as it's a single assignment. Next, the main computational work happens in the for loop, which iterates from 1 to n1. This loop runs n times for an nx3 grid. Within each iteration, we compute the new values for 2_color and 3_color using simple arithmetic operations, such as addition, multiplication, and modulo, all of which are constant time operations. These updates and assignments also take 1 for each iteration. Finally, the return statement calculates the result as 2_color plus 3_color, %mod, which is another 1 operation. Since the loop dominates the overall runtime, the total time complexity of the solution is n. Now, let's consider the space complexity of the solution. The algorithm uses a fixed number of variables to store intermediate values, such as 2_color, 3_color, new_2_color, new_3_color, and the constant mod. Each of these variables occupies 1 space, and the total number of variables does not depend on the size of n. Importantly, the algorithm does not require any additional data structures, such as arrays or matrices, to store intermediate results. This means the memory usage remains constant regardless of the size of the input. Therefore, the overall space complexity of the solution is 1. Let's compare this optimized dynamic programming solution with a brute force approach. In a naive solution, we would generate all possible ways to paint the nx3 grid. Since there are 27 possible combinations of colors for each row, this approach would involve recursively validating each combination to ensure adjacent cells meet the constraints. For n rows, this would result in a time complexity of 27 to the power of n. As the number of combinations grows exponentially with n. Additionally, the recursive stack would grow linearly with the number of rows, leading to a space complexity of n. In contrast, the dynamic programming solution eliminates redundant computations by only maintaining the counts of valid patterns for the current and previous rows. This reduces the time complexity to n, as we process each row exactly once, and the space complexity to 1, since we only use a fixed number of variables. Notably, the best, average, and worst cases all have the same complexity in this problem because the algorithm processes each row in a uniform manner. Finally, let's mathematically justify the n time complexity of this solution. If we let n represent the total time taken for n rows, the initialization and final computation each take 1. The main for loop iterates n1 times, and each iteration involves constant time operations, such as arithmetic calculations and variable assignments. This gives us n equals 1 plus n1 asterisk 1 plus 1. Simplifying this, we see that n scales linearly with n, resulting in n time complexity. For space complexity, the reasoning is straightforward. The algorithm uses a fixed number of variables, and their count does not grow with n. Thus, the space usage is constant, leading to 1 space complexity. When tackling this problem, there are a few common mistakes to watch out for. First, a frequent error is ignoring the vertical constraints. Many solvers focus solely on horizontal constraints, like ensuring that no two adjacent cells in the same row share the same color, but they neglect the rules for adjacent rows. This can lead to invalid solutions where rows violate the vertical coloring constraints. Another mistake is attempting a brute force solution for large grids. Generating every possible grid configuration and then filtering out invalid ones is highly inefficient as the number of combinations grows exponentially with n. This approach quickly becomes computationally infeasible. Lastly, failing to pre-compute reusable states can significantly slow down your solution. For instance, valid row configurations can often be reused across rows, and neglecting this leads to redundant computations that waste time and resources. In addition to those, there are two more pitfalls to be aware of. One is setting up an incorrect base case in your dynamic programming solution. If the first row isn't initialized properly with respect to the coloring constraints, the entire recursion or transition logic will produce incorrect results. A solid foundation for the base case is critical. Another issue is misinterpreting the problem constraints. A common misunderstanding is assuming diagonal adjacency rules, which don't actually exist here, or overlooking that the grid always has a fixed width of 3. Such misinterpretations can lead to either invalid solutions or overly complex implementations that aren't necessary. Now, let's consider some insights that are particularly useful in interviews. This problem is a classic example of recognizing overlapping subproblems, which makes it an ideal candidate for dynamic programming. Pre-computing valid row configurations and their transitions is another key optimization that can save significant time. Additionally, modular arithmetic is often required to handle large results, especially when the solution involves iterative computations where values can grow rapidly. Modulo 10 to the power of 9 plus 7 is commonly used in these scenarios. During interviews, you might be asked to discuss ways to optimize your solution. For example, you could be asked about reducing the state space or improving time complexity. Be prepared to explain the trade-offs between a bottom-up dynamic programming approach and a top-down memoized recursive solution. Finally, don't overlook edge cases, such as grids with a minimum size of n equals 1, grids approaching the upper constraint like n equals 10 to the power of 4, or cases where the constraints drastically limit valid configurations. This problem shares similarities with several others, so practicing these can help you build a stronger foundation. For instance, LeetCode 1931, painting a grid with 3 different colors, involves similar rules but varies in scope. Problems like LeetCode 256 and 265, PaintHouse and PaintHouse 2, also explore dynamic programming and constraint-based coloring. Even LeetCode 691, stickers to spell word, although not directly about grids, involves state transitions and combinatorial logic. As for alternative approaches, one option is dynamic programming with state compression. Here, you pre-compute all valid row configurations and use a DP table where each state represents a valid row. While this requires more pre-processing time, it significantly accelerates the overall runtime for large grids. Another approach is recursive backtracking with memoization, where you generate valid rows recursively and memoize overlapping subproblems. This method is easier to implement but tends to be slower than iterative DP due to recursion overhead. Finally, another advanced approach is using matrix exponentiation to handle the transitions between rows. In this method, you represent the transitions as a matrix and use matrix exponentiation to compute results for large values of n efficiently. While this technique requires a deeper understanding of linear algebra, it offers optimal time complexity for very large grids. This makes it a powerful tool when working within strict performance constraints. That wraps up problem number 1411, number of ways to paint n times 3 grid. We discussed the brute force approach and its inefficiencies, while highlighting the importance of optimization. Thank you for watching, and be sure to like and subscribe for more coding tutorials.